In this video, I'm going to go over section 10.4 and 10.5 and go over some examples from each of the things that you should have learned from your investigations. So in the first investigation, I asked you to investigate the relationship between an inscribed angle and the central angle and also the intercepted arc of both of those angles. So hopefully you found that the intercepted arc inside of the inscribed angle is twice as big, and so that angle is 1/2 the measure of that intercepted arc. So in this case, angle 1 is 1/2 the measure of arc AB, since that's the intercepted arc, and vice versa, measure of arc AB is equal to twice the measure of angle 1. So in this problem here, what we need to do first in each case is find the measures of the intercepted arcs for those inscribed angles. Again, we know those are inscribed angles because the vertex is on the circle and the sides of the angle are both inside the circle. So according to this, we know that the measure of AB is 140. We know that the measure of BC is 100. And even though it doesn't look like it, we know that the measure of AD and DC are equal. That makes the entire circle. So these two together give us 240 degrees. If we subtract that from 360, we get 120 degrees, which means each of these arcs is 60 since they're equal to each other. So if we want the measure of angle 1, we can see that this is the intercepted arc for angle 1. So it's going to be 1/2 the measure of arc AD, or 30 degrees. To get the measure of angle 2, that is the intercepted arc for angle 2 is DC, because that's inside of angle 2. So the measure of angle 2 is equal to 1/2 the measure of arc DC, which is also 30 degrees. To get the measure of angle 3, that intercepted arc is BC. So that's going to be 50 degrees. Angle 4, its intercepted arc is AB. So that's going to be 70 degrees. And angle 5 is also intercepting arc BC. So it's also going to be 50 degrees. That leads us to this investigation where we had two angles, angle B, DBC, and angle A, DAC, intercepting this same arc here, DC. So because angle B is 25 degrees, that makes arc DC 50 degrees. And since this is also intercepting it, that is 25. So just like in the last example, two inscribed angles that intercept the same arc in the circle are going to be congruent. So you don't need to find the measure of this arc to be able to find the measure of this angle. As long as we know they're intercepting the same arc, we can say that those are congruent to each other. In this investigation, this is a semicircle. Semicircles are 180 degrees. And so this inscribed angle is going to be half of that, are 90 degrees. So any inscribed angle that intercepts a semicircle is going to be a right angle. So first we're going to take the idea that the two inscribed angles in the same circle that intercept the same arc or congruent arcs. So that works also if you go back to this. These two intercepted congruent arcs, so they were congruent. These two intercepted the same arc, so they were congruent. In either of those cases, those angles are going to be congruent. So here, because angle T and angle U intercept the same arc, SV, I can say that those are congruent to each other. And get x equals 20. And so when we plug that in for the measure of angle T, we get 3 times 20 minus 5, which is 55 degrees. We can check that to make sure that we did our algebra correctly by plugging that 20 in here. So we get 40 plus 15, which is also 55. So we did make angle T and angle U congruent to each other because they intercept the same arc. We did not need to know this arc measure in order to find those angle measures. The next idea that any inscribed angle that intercepts a semicircle is a right angle. So here we know that angle 1 and angle 2 have to be complementary because this is a diameter. So this is a semicircle. So angle E is intercepting a semicircle and is a right angle. That makes this triangle a right triangle, and the acute angles have to be supplementary. So the measure of angle 1 are complementary, and the measure of angle 2 have to equal 90. So we can make that equation: 12x minus 8 plus 3x plus 8 equals 90. So x is going to equal 6. And then we can plug that in. So the measure of angle 1 is going to be 12 times 6 minus 8. That's 72 minus 8, or 64 degrees. And the measure of angle 2 is 3 times 6 plus 8. That's 26 degrees. And then we can see together those two add up to 90. When we look at angle 4 and angle 3, they tell us that arc AB and BD are congruent to each other because arc BD is the intercepted arc for angle 3. Arc AB is the intercepted arc for angle 4. That means those angles are going to be congruent. Also, this is a semicircle, which makes angle B a right angle. And so this triangle right here, ABD, is a right triangle. So we have a right triangle where the acute angles are congruent. That makes them each 45. In this investigation for 10.4, I asked you to figure out the relationship between these angles in this inscribed quadrilateral. So we're going to use what they tell us. So angle B is 80 degrees. Angle B's intercepted arc is ADC. So that has to be 160 degrees. Well, angle D's intercepted arc is the rest of the circle. So 360 minus 160, which is 200. Angle D is going to be half of that, so that's going to be 100 degrees. Also, we know that angle C is 40. Its intercepted arc is DB, and so that's going to be 80. The rest of the circle, DCB, is 360 minus 80, which is 240. And so that makes this angle right here 100. Sorry, that's 280. And that makes this angle right here 140. So then hopefully you noticed that these two angles add up to 180. These two angles add up to 180. And so when you have a quadrilateral inscribed in a circle, the opposite angles of that quadrilateral are going to be supplementary. So anytime you see a quadrilateral and you have one angle, you can know that it's a quadrilateral inscribed in a circle, and you know the measure of one angle, you can find the measure of that opposite angle by subtracting from 180. All right, in this investigation, you should have noticed that the sides of the square, the sides of the hexagon were tangent to the circle. Also, they are tangent to the circle. All right. And if you draw in a radius to that point of tangency and measure that angle there, you would see that that was a 90-degree angle. This is also the same when we had a hexagon. So I wanted you to see that anytime you have a radius drawn to the point of tangency of a tangent line, no matter where that what that tangent line is, a side of a shape, if it's just a tangent line all by itself, that will always be a 90-degree angle there. So any radius drawn to the point of tangency is going to be perpendicular to that tangent line. Also, that works backwards. If I want to make a tangent line to a circle, the only way you can do that is to draw in a radius and to construct a line that is perpendicular at the point of tangency. Otherwise, you can't be certain that a line is tangent to the circle, but as long as it's perpendicular to the radius at the point of tangency, it has to be a tangent line. So later on, you're going to do investigations where you have to construct tangent lines. This is the only way to construct a tangent line. Make a circle, draw in a radius, and at that point of tangency, construct a perpendicular line. So here in this problem, I can see that this radius is drawn to the point of tangency right here for this tangent line JH. So we have a 90-degree angle right there, which makes a right triangle. 8 is only for KH here, because the hypotenuse of my right triangle cannot be smaller than this side here. This is another radius. So since my radius is length of x, that radius is also length of x. So now I can use the Pythagorean theorem and say that x squared plus 12 squared, and then my hypotenuse is going to be x plus 8 squared. Be careful when you are foiling on this side that you actually multiply that out. This is the same as x plus 8 times x plus 8. So there's a middle term. because we have 8x plus 8x. So when I move this x squared to the other side, the x squareds cancel. So I get 144 minus 64, which is 80. And so x is going to equal 5. In this problem, we want to show that KL is tangent to the circle. In order for that to be tangent, this has to be a right angle. If that's a right angle, then the Pythagorean theorem has to work. Once again, we don't have the hypotenuse, but we recognize that this is another radius, so that's 8. So the hypotenuse length is going to be 17. And we add those together. So I can say 15 squared plus 8 squared and that gives me 289. When I square 17, I also get 289. That means the Pythagorean theorem works. A squared plus b squared does equal c squared. So yes, that has to be tangent because this is a right triangle. And when the radius drawn to the point of tangency is perpendicular to the line, it must be a tangent line. Same here, this radius has to be 3, which makes this hypotenuse 5, and 3 squared plus 4 squared is equal to 25. 5 squared is also equal to 25. So yes, LM is tangent. MN is tangent to the circle because we have a right angle here. In the last investigation, you were supposed to construct this and check the measures of these two tangent segments, these red segments here, and you should have found that those were congruent. So anytime you have a segment drawn from the point of tangency to the point of intersection, those are called tangent segments. Those tangent segments are going to be congruent to each other. So in this picture right here, these are a pair of tangent segments drawn to the same intersection point. They're going to be congruent to each other. So x equals 20. A polygon is circumscribed about a circle if every side is tangent. So in that original investigation that I had you do for this, anytime you have polygons circumscribed around a circle, the sides of that polygon are tangent. So they don't have to tell you that they're tangent. They just have to tell you that the polygon is circumscribed around the circle. So here, this triangle is circumscribed around the circle. So I know that every side of the triangle is tangent to the circle. That means that from E to D and from D to F, those are a pair of tangent segments that go to the same intersection point. They are congruent. B to A, F to A are also a pair of tangent segments to the same intersection point. And E to C, B to C are also a pair of tangent segments that go to the same intersection point, so they have to be equal. So I know if those are equal, that length is 6. If these are equal, this length is 19. And I know that EC is equal to DE plus AF. So that's 6 plus 19, or 25. And this one also has to be 25. So to add all those together to get the perimeter, $100.